UI VI, sorry, first UI VI UJ VJ. Okay, horizontal displacement node I, vertical displacement node I, horizontal displacement node J, and vertical displacement U I prime, and then UJ prime, and then elongation, strain, stress, and then finally elemental force, which is capital F. Okay, for node I and node J for element 1 and 2, so that means for element 1, node I 1, node J 2, that means UI here is U1. U1, so U1 is there. E1, there, value there. UJ, okay, J is 2, that means U2. U2, we take this value 0. Don't take this one because this is with a little bit of error there, a little bit of very small number, but actually this is 0. Just put 0 there. That 0 is the actual value, and V2 equals to 0 as well. Here, okay, U not I1 same. Okay, 3 now, 0. Okay, VJ3 0 as well. Okay, check back. So 1 not 1 UI BI, okay, correct. 1 and 2 0, okay. Okay, so UI prime and UJ prime using the formula, this formula here. Okay, we need to find UI prime and UJ prime. CUI plus SVI, CUJ plus SVJ. This one UI equals to C for element 1 multiply UI, this one, plus S plus, multiply VI. Okay, if you drag this down, it will automatically calculate for element number 2. Okay, if you drag this down, it will automatically use C and S, this C, this value C and S, and U and VI here for element 2. See, automatically it will use this red, green, blue and purple there. We don't have to type the formula twice. Similarly here, equals to C find C for element 1, multiply by now uj, uj plus S times Vj. There. 0. It's 0 and then you just drag down 0 as well. And then elongation equals to uj prime minus ui prime. That's the elongation. Okay, you drag down, we get elongation for element 2. Strain equals to elongation divided by length of element. Find L here, L. And then drag down. That's strain for element number 2. Stress equals to strain multiplied by Young modulus. Okay, and then finally F equals to stress multiplied by cross-section area, A. That A there. Okay, and that's it. So finish. So we got all the answer. If you forget how do we get this? Actually, we use this formula here: elongation, strain, stress, and F. Okay, any question? Ada soalan? Ada apa-apa soalan? Unit, Newton, put the unit on top. This is stress, Pascal, or Newton per meter square. Strain, no unit. Elongation in meter. Okay, and then here is in meter as well. That's as far as unit is concerned. Okay, any soalan? Any question? Please ask question. Any maybe any there's a parts that you don't understand. I can repeat it for you.
Doktor.
Yeah.
Doktor repeat yang apa constraints by DEM lah doktor.
Uh,
Sikit. Yang
yeah. Yang mana? Direct elimination method?
constraints by DEM.
By direct elimination method.
Itu. Dekat table tu.
Okay.
Cakap ke doktor dapat yang 0100 yang untuk V1 U2 tu.
Okay.
Macam doktor dapat.
Okay. If you remember from the last lecture, this is how we apply constraint by using direct elimination method, DEM. To the place, to the location that we want to apply the constraint, or the degree of freedom, what we call it, the degree of freedom we want to constrain, we need to put 1. Automatically, we put 1. In our case here, go back to the figure. Okay. In our case here, node 1, we constrain node 1 50 millimeter downward. So that means 1 constraint there. For node 1, 1 constraint. Vertically downward, that means V1. V1 equals to 50 millimeter downward. U1, which is horizontal displacement node 1, no constraint. Just leave it like that. For node 2, fixed to the wall. So that means we constrain the U and V. U2 and V2. Similarly, to node 3, we constrain U3 and V3 because node 3 also fixed to the wall in X and Y direction as well. So we have 5 constraints that we need to apply to our equation. Now we go back to the equation. First V1, remember 50 millimeter downward, we want to put the constraint. So V1, this is the location, yeah, V1 and V1 there. So this is the location. This when we want to apply the constraint, we look at the label. This is why I put the label so that we can see clearly where we want to put the constraint, which cell correspond to which node. This is the point of this label here, so that we can see clearly. Okay, so for V1, node 1 vertical motion, so we put 1 there, and then this value 0, 0, this is automatically become 0. Whatever the value, whatever the initial value here is, remember, this is the initial value. We put 1 there, and then all others value there automatic become 0. And then here, initially 0 there, we put the value of the constraint, which is minus 50 millimeter downward, type minus 50 E minus 3. E minus 3 means milli. That's for node 1, V1. And then node 2 and 3 fits all. We fix all the degree of freedom in X and Y direction. So U2, V2, U3, V3 follow the same step. Put 1 for horizontal displacement of node 2, U2. See this label here, U2 there, and then U2 here, U2 here. So this is the location. Put 1 there, and all others location then you need to make sure become 0. Only here 1, and then all others at the same row, okay, change to 0. Even though initially it has value there. See this, yes, value, you just change it to 0. And then make sure value here 0 because we want to make our U2 equals to 0. Okay, follow the same step. V2 equals to 0, U3 equals to 0, V3 equals to 0. And then just make sure all other values, make sure change to 0. See, this is minus 315, we change to 0. And here, okay, change to 0, even though it has a value initially. Okay, clear?
So doktor, yang first row tu tak payah ubah apa-apa ke?
Okay, this row, this
Ah,
one you don't have to change because no constraint, right? There is no constraint horizontally at node 1 because node 1 only constraint vertically. It can move freely horizontally. Secara horizontal dia boleh move freely. So we don't have to put any constraint.
okey.
Okay, kita put constraint where we want to fix the motion. We want to fix it to the wall so that it won't move. So value it becomes 0. We want to fix it so that it only move 50 millimeter downward. So that means constraint. Other than that, you don't have to change anything. Something like this, you don't have to change anything. Just ignore it.
Okey, faham doktor.
Okay.
Okey.
Ada lagi? Any more question? Please ask question lah. Saya open lah. Tanya soalan. So I want you to really understand this. Okay, so that you can do excellently in test 1 because axial element trust element, things easy chapters.
Doctor,
Yeah.
one more question for the PM method. So it's the same that we just plus the C for all the constraint.
Okay. For penalty method, PM. So where we want to apply the location we want to apply constraint is different to the direct elimination method. For direct elimination method, we put one. But for penalty method, whatever value here, okay, whatever value there, okay, we need to plus C, which is very big value. This part here, you need to plus with C, and then here, okay, under the F vector, load vector, whatever the value there, you need to plus with C multiplied by the constraint. C times constraint. Here, whatever value C times the constraint. Since our constraint here is minus 50 millimeter. Here, okay, equals to whatever the initial value there plus C multiply the constraint. But since all this constraint equals to 0, if you remember, the constraint here is 0. Okay, so C multiplied by 0, 0 plus initial value here is also 0 as well. You see, initial value 0. So 0 plus 0 equals to 0. Okay, clear?
All right.
Okay, so maybe I think maybe we put constraint U2 equals to V2 equals to U3 equals to V3 equals to 0. So make it more clearer for this part here. Okay, ini maybe last question before we scan the attendance. So this I will share with you after this example. Okay, to put last there. You already have this, right? The question. I hope you get the clean one, not this with my scribble. I don't know whether I share with you the one with the scribble yang saya dah conteng or is it the one without scribble? Okay, good. Okay.